Okay, so in this lecture, let's go ahead and start drawing some rectangles. There's one thing that I want to do first. We are going to create a new file in our project. So I'm going to open up this. I'm going to call it types.h. Now you'll notice this is the first time we've made something that ends in a .h instead of a .c. The difference is really not too substantial. The main difference that we care about is the fact that all of these things are .h files, and we are going to use a .h just essentially to say, hey, this is just something that's going to include like definitions of things, like maybe variables or the names of functions, and it's not actually going to include a lot of the code itself. Right now, it could, but there are reasons that we don't want it to. Right now, we don't care about those reasons because we aren't going to do a whole lot with this file that involves that. What I am going to do, though, is have this H file include some H files. One of the things it's going to include is this file called standard int, and then we're also going to do one that's going to be, I think it's int types.h. And we'll see why we care about that in just a second. So right here, this is called a type def. And what this is going to let us do is replace, or not even replace, but just use one type name that we are defining as if it were another already defined type, right? So, for instance, let's just say that I had something that I want to be an int, but I want to call it its own thing. Like, I want to call it health, right? Now, that would let me do something if I said, struct player, I could say health HP, right? Instead of saying that it's of a type int, I could say, hey, it's of type health. Now, maybe I wouldn't want to do it this way. I mean, you could. I don't really see an advantage to it. But it lets you do things like that. What I do want to do, though, is go ahead and define convenient names for types that maybe give us a little more information about them. So, for instance, we have a type called int, right? And then we also have a type called unsigned int, right? That would be from 0 all the way to positives, right? It never goes negative. But maybe I don't like typing unsigned int every time. Maybe, I find that a little verbose. And I want to type something like uint, right? Or maybe even uint32, which tells me, hey, it's 32 bits, right? And then uint8, which would tell me, hey, it's 8 bits, and it's unsigned, right? Well, that's what is in here. If I look at standard int .h in C, we can go ahead and look. See, this is where things like signed and unsigned are specified. And we see we have this list of types with these underscore t's. So we see, oh, hey, here is a signed int that's 8 bits. Here's an unsigned one that's 8 bits, right? Well, what I want to do is say, hey, if I have an int 8t, I want to just be able to call that int 8, right? And if I have an int 16, I want to call that int 16, int 32, int 32, and then if I have one that's 64, I want to say 64, right? And then I want to do that same thing, but I'm going to replace int with uint. And then I'm going to have a type def where I say, oh, well, no, I guess that's all I care about. Although I can go one step further. Actually, this maybe illustrates some of the cool depth of the idea. Where now I have an int 8. Well, I can just say that this is a signed 8-bit number, right? If I have a type def in 16, that's S16. In 32, S32. In 64, S64. And then I can say, do the same thing. And then I'm going to say S to U, right? So if I'm writing uint8t, I'm saying, hey, I have an unsigned number that's 8 bits. If I write uint8, I'm saying, hey, I'm using uint8, but it's a uint8 underscore t. And if I just say u8, I'm saying, hey, it's this, which is this, right? So that lets me do, it just lets me define my types in a way that I'm comfortable talking about them and talking about writing them, right? So we can go ahead and include that file now. We are going to include it right here. And instead of using these angle brackets, we're going to use quotes because it's a file that we made that's in our project directory, right? So it's not somewhere stored, in the operating system's file directory. It's just in our source code, right? So let's go ahead and look right here. We should be able to compile, and it works. And now, if I want to say, instead of saying unsigned char, if I just want to say uint8 and cast it to a uint8, and it's a size of a uint8, then I should be able to do that, no problem, and our program still works. So that's just a little nicer. Again, it's kind of weird that we think of these components of a bitmap as unsigned chars. Like, we don't really, like, they aren't chars, right? They're only similar in the fact that they're the same size. So we just maybe don't like using the term char for that, right? Another nice thing about it is it makes it very easy for us to just like look at our data and know the size of it. Like if I say unsigned char, it's only because I have a lot of experience programming in C that I know what the size of that is. The same thing with int, right? Or if I have an int 32, I just know, hey, this is a number that is 32 bits. And, I don't have to guess, right? If I say this, I say, hey, it can't be negative. And that's nice because, like, pixel size. How could pixel size be negative? It doesn't even make sense to have that, right? Same thing with screen width and screen height, right? What does it mean to have a negative screen width? So we can go ahead and, define a few of these things in that way. And you see nothing terrible happens. Our game is still running. All right. So now what I want to go ahead and do is make a function that's going to draw a rectangle. So it's going to be a void. I'll call it draw rect. And, it's going to take some stuff. One thing that I know it's going to take is it's going to take a pointer to the bitmap, right? Because we want to go into our bitmap, look in it, and draw some stuff there, right? So what we want to do is we also want to say, all right, and again, we can specify these as uint32s because, again, just having a negative position doesn't make a lot of sense. Maybe for drawing a rectangle. Maybe it does. Maybe we'll think about that later that we care. Like, we can imagine a rectangle that's drawn at position -10, -10, but is 100 by 100. Well, it would be off the screen a little bit, but not completely, right? But for right now, I don't think we care about that. So we'll call this start X and uint32 start Y. We'll call this width, and we'll call this height, right? So we want to know the dimensions of it. And we want to also go ahead and say, I think, what the color of it is. So I'm going to go ahead and make this thing called color. Say struct color. And this is going to have a uint8 red. In fact, I'll just call them R. Uint8 green, uint8 blue. I will say uint8 alpha, right? And yeah, I'm going to pass that in. I'm going to say color, right? And I need to say struct color. Okay, so these are the things that I care about when I'm drawing the rect, right? This is kind of all of the information that I need to make it work successfully. Now what I want to go ahead and do is find out where I should start drawing that pixel. So we have these start X and start Y, which is going to be in pixel space, right? So it's going to be, in our case, it's going to be a number from 0 to 800, technically 0 to 799, and then 0 to 449, right? So this is where using pointer arithmetic, like I demonstrated a few videos ago, gets very cool, right? Like if we go back and we look at our string length function, you can see we're just, we're taking the address and we're adding numbers to it, right? So what we can do here is find, let's see, do I have an art program on here? I believe I do. I'm going to just go ahead and draw a diagram because I think this will be a good way to start off. Okay, so see, I'm going to make this a little smaller. So we have our screen right here, right? Guess I can do that, right? All right, so let's just say that each of these rows is a row of pixels, right? And you'll have to excuse my terrible drawing. I'm not much of a better drawer if I had a pen, but I'd be a little better than with a mouse here. So we see we have each of these rows, right? So we have, here is our X, and here is our Y. And so we're starting up in the corner right here. This is like 0, 0, right? And then here is our maximum X along here, and here's our maximum Y. So what I want to go ahead and do is find, based on the X position, based on the Y position, I want to go ahead and find which row I'm starting to draw at, right? Because here's like pixel 0, here's pixel 1, pixel 2, pixel 3, pixel 4, 5, 6, 7, 8, then 9, 10, 11, 12, 13, 14, 15, 16, right? Etc. So when I'm drawing my rectangle, I want to find the row first. And then I want to start drawing and filling in that row. And then I'm going to move to the next row and start at the appropriate location, right? So, and keep in mind, each of these things is 4 bytes big, right? So here's 4. It's going to be, well, actually, you go ahead and undo this. This is 0, 4, 8, 12, etc. And then here, it's going to be, what, if these are 16, so 16 by 4, that's going to be, here's like 64, right, etc. So we have an address that's just pointing to our bitmap. And what we want to go ahead and do is convert that address, not convert that address, but we want to go ahead and move into that address to be at the row where we should be, right? So we're going to make a new pointer, and we're going to call it row. And we're going to say that it equals the bitmap plus something, right? So we want to know how many pixels to move along to find the correct row. Well, if I go back to our image right here, let's say I want to draw something on row Y, right? Which I realize now kind of looks like an X, so we'll move that back. So yeah, I want to draw something on row 1, right? Starting on row 1. Well, okay, so what I need to do is take the address, which is starting at 0, and I need to add 64 to it, right? So I know that just from looking at the diagram, but we can think about that algebraically, because, if this is 128, right, and then this would be 256, etc. I know, hey, if I want to draw on the first row, I want to say, all right, take my y, which is going to be 1, and multiply it by the number of bytes on a single row, which in this case is 64, right? So if I take 1 times 64, I would wind up at the address of the pixel on the second row. Same thing if I want to go on the second row, or sorry, if I want to go on the third row, which is the row at index 2, right? So not 0, not 1. We go to index 2, row 2, which is technically the third row. I would take the y position, which is 2, and I would multiply it again by 64, because I know that this thing is 64 bytes long. So we want to say, we take the start y. I'm going to go ahead and put this in parentheses. Start y times the row length or something like that. Maybe we don't have a technical term for it. Luckily, though, I do know a technical term, and it is called the pitch. So the pitch is the number of bytes for one row. So let's also go ahead and pass that in, right? We'll say pitch, right? So we'll do start y times pitch. So we need to go ahead and define pitch right here, which we can do with all of these other things. We can say, all right, the pitch equals the pixel size times the screen width, right? So this is going to give us the row where we want to start drawing our pixels. Now what we want to do is we want to loop over all of those pixels, right? And for each pixel, we want to go ahead and we want to loop over all of the rows that we want to draw, right? So we have our starting row, but we want to know, okay, where is the second row? Where's the third row from that initial position, right? So, and each time through, we're going to say that the row plus equals the pitch. So we can go ahead and see why that would be. So let's say we want to draw something that's going to be three tall, and we wanted to start it at row 1, right? So it's 64 right here. Well, so when we start drawing at our row 64, we're going to set our initial value to be the start y, which is 1, times the pitch, which is 64. Then we're going to draw some number of pixels to fill that row out, right? And then when we get to the end of that, we're going to say, okay, hey, take whatever my address is and add the pitch to it. Or, sorry, take whatever the address of the row I'm on is and add pitch to it. So now we're going to get 128, right? Then we're going to fill out some stuff here. And then we're going to say, hey, take the address of my row and add pitch to it. And we're going to get 256. We're going to finish out some stuff. We're going to hit the end of our while loop, right? Because, if our height is 3 and y is now 3, then we're done, right? Okay, so now what I want is I want a pointer that is telling me the pixel that I'm at. So this is going to be an address pointing me to a pixel. And we can say at the beginning, it's just going to be starting at row, right? But then we know that every time we move forward, every time we move 1 pixel to the right, we want to move 4 bytes, correct? So what we will do now is we'll do another loop. We'll say x equals 0 and x is less than start x. Sorry, x is less than width x plus plus, right? And here we'll do some stuff that we haven't specified yet. So that's working here when our x is 0, right? Because, if we want to just draw something in this box, we're always going to start at the row, right? But let's say that we want to draw something, I don't know, in this box, right? So we have our correct row, but we want to go ahead and move some pixels over, technically 2 pixels over, and start drawing there, right? Well, the way that we are going to do that is very similar to the way that we did this, right? Where here we're moving an entire row at a time, but here we're just going to be moving a pixel at a time. So we're going to be moving by 4, right? So we can take our row and add 4 times our start x to it, right? If we go over here, we can see, well, hey, if our start x is 0, we aren't going to move over at all when we start drawing our rectangle here. If our start x is 2, we're going to start at row 64. Then we're going to move 4 bytes over and get right here. And then we're going to move 4 bytes over and get right here. And now we're going to start drawing. And we're going to draw, maybe 3 bytes for a width of 3. So we're going to be drawing a 3 by 3 rectangle, right? Okay, so hopefully all of that makes sense to you. If it doesn't, what I would strongly recommend is getting out a drawing program or a piece of graph paper or something like that, and just try a very simple grid. It maybe doesn't even have to be as big as this. Maybe do like an 8 by 8, right? And just go ahead and try experimenting with different values of x and y and moving by pixels and just starting to develop a feel for how this works. And again, hopefully the pointer math of that makes sense, because since we're dealing with bytes, we can just always move, 1 byte at a time, right? All right, so now what I'm going to do is we have a pixel, right? So our first pixel is going to be representing there's a technicality here. Let's just say for right now, our first pixel represents one of the components, right? So you can kind of sense the ominous change there, right? So the first pixel represents one of these, the second pixel represents another, etc. So let's just say right here, we're going to, again, dereference the pixel. So take whatever byte we're pointing to and then change the value of it. And so we're going to say it equals color.r. Then we're going to say, all right, hey, take the pixel, and we're going to add 1. So we're going to move 1 address over. So if we're looking at it right here, let's say we're drawing on this pixel, we're going to set that pixel, move over 1, set that pixel, move over 1, set the pixel, move over 1, and then move over 1, right? And just keep doing that. So pixel color.g pixel plus plus, I'll just copy paste that, right? And right now I don't even think we care about setting the pixel for the alpha. Well, I guess we can. It doesn't matter. We'll set it. All right, let's go ahead and compile that. Wow, no errors. Amazing. So let's go ahead and call this function right here. So I'm just going to say, hey, before we enter our loop for the game, let's just go ahead and just call draw rect. So I'm going to pass in the bitmap. And just, by the way, if you're wondering why we aren't passing in the image and we're passing in the bitmap instead, the reason for that is this is kind of a perfect example of code that we don't really care about being part of the platform or the operating system level. This is totally in the game sphere, right? So all we care about is just getting a pointer to some bytes that represent our bitmap. And then the operating system is what's going to care about, what we do with those bitmap or with those bytes in the bitmap, right? So we'll pass in bitmap, we'll pass in pitch, we'll pass in a 0 and a 0, so we'll start in the top left corner. Let's do, 1550. And then, we want to make a color, right? So let's make a struct color, I will say, hey, color.r equals 255, color.green equals 0, color.blee equals 0, color.a equals, we'll do 255. We'll say it has a alpha, a full alpha, right? So it's not transparent at all. So now when I run that, you see we get this cool guy up in the corner right here. So that is pretty neat. And we can go ahead and change the size by that. So let's do like 80 and 45, like that. And etc. You know, we could actually even go ahead and draw multiple of these, right? So let's draw that one at 0, 0, and draw this one at, I don't know, we'll do 160, and we'll do that, you know, we'll do it at 0 also. So now we get it sort of far apart. Here, we'll do 160, we'll draw another one, let's do 160 and 80, like that, right? So, see, we get that one right there. Okay, that is, I think, pretty neat. What we can now do is say, let's see, I'm trying to think. Well, let's just we'll sort of cheat right now. Let's see what happens when I type A. It's 38, right? Okay, so let's say if event.xkey.keycode equals 38, then I want to go ahead and let's make a new color, struct color 2. We'll say color 2.r. I'm just going to go ahead and write this all on one line, by the way. Oh, and hopefully you realized that maybe a weird thing was going on. 2 dot equals 0, color 2.a equals 255, right? So I just went ahead and put it all on one line. And I don't know, we'll draw this one at like 320 and 80, right? So now when I press A, we get this cool green cube, right? All right, so the issue is that these colors are actually in the opposite order from what I originally mentioned. So the order of our bitmap is actually going to be, blue, green, red, alpha. So blue, green, red, alpha. So by changing this right here, what we're saying is, hey, we still want to think of colors as RGB. You know, for whatever reason, I don't know if like actually on LCD that's the order that they're in, RGB. Again, you know, Linux is pretty old. You know, it's the traditions it's coming from are even older. So maybe back in the day, the pixel or the component order was blue, green, red. I'm not exactly sure. It's the same way on Windows, though, so there's clearly some sort of reason for it, whether or not it's traditional or practical. So now we have red, 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 and then when we press A, we'll still get this green cube, right? So, yeah, that all looks pretty good. One more thing that I want to try is say, let's say we have this position. We'll call it rect position. We'll say rect position.x equals 0. We'll say rect position.y equals 0, right? And then we can say every time you press A, we're going to say rect position.x plus plus, right? And now we can go ahead and draw. We'll just say every time through, we draw a rect at rect position.x and rect position.y, right? And if I keep drawing that, see, we're getting that right there. I'm going to go ahead and say struct color, rect color, right? And again, I'm going to go ahead and make this, let's try maybe a nicer color. We'll say it's going to be 128 red, 64 green. All right, cool. So you'll notice that I keep pressing space, and it looks like we're just drawing more and more, right? It's not like a position that's growing. I mean, sorry, it's not like a position of something that's moving. It's just growing. So if you're curious about why that is, I'll go ahead and say pause the video right here and think about it for a few minutes. Go ahead and maybe look at things we were doing with memory earlier in a few videos ago. And if you get bored of thinking about that, I can go ahead and tell you right now. So the reason is when we draw into our rect, we just go ahead and we look into the bitmap, we see which pixels we need to set, and we change their value, right? The issue is that we're never actually, we're never clearing the bitmap to be a value again, right? So like, let's say we go back to set this to 0, right? So now, maybe this is clearer. So the issue is that we start with all of these pixels being black. And we start, we draw a rect in the corner and it's brown, right? But as we keep moving, we aren't going back and setting those pixels to brown. So what we actually want to go ahead and do is just say, hey, right here, we're going to do a memset on bitmap. We're going to set it all to 0, and we're going to do bitmap size, right? And we're going to, every time we're going to draw all of these rectangles, right? Oh, what did I do to change the color of all of those? Is that just crazy? No, all of those are definitely brown now. Were they not before? If I use rect color, what am I doing wrong here? It seems like, oh yeah, okay, duh, this is so silly. Because I should be setting rect color right there, right? Not color. So I created a new struct, but I just went ahead and set the values to the same thing, right? So now we have this cool brown square moving around, and these red ones, which are stationary, right? And every time I press A, or wait, it seems to be happening no matter what key I press. Why is that? We definitely shouldn't be changing the X position of the rectangle, I don't think. I mean, it doesn't even make sense that we would be. Let's go ahead and say that we're going to print out the position of the rectangle. well, we're always hitting that, even though... Oh, haha. Oh, this is really neat. Okay. I mean, it's awful, but I'm glad. So the issue is that we're saying event.xkey.keycode equals 38 and not is it equal to 38. So we're assigning it to 38, which is always going to be not 0, right? So it's always true and it's always going to fall through, right? Into that conditional. So now I'm pressing space, nothing's happening. Now I'm typing A and something's happening. Now I'm typing something else, nothing. Escape. Cool. So yeah, go ahead and play with that. You know, we could try something like, what if we say x plus equals 20 every time, right? We feel like this guy's moving a little slow. Cool. Something really bad is about to happen. At least I suspect. Oh, wow. Nothing really terrible happened that time. I was expecting the game was going to crash. It does seem rather resilient. What we have done, though, is we haven't really wrapped around. We've gone on to a new row. So that could be a pretty interesting thing to look into. But it's weird. Yeah, you see that our position is now 10,140, which shouldn't be a valid pixel. So go ahead and play with it. See if you can detect anything like that that's maybe a little unexpected or strange. And go ahead and shoot me an email and if you have any questions. And I will be talking about some of these things in the next video.